Hey everyone, we are Team Technova and we made a robotic arm. My name is Harsh
I am Rhythm.
I'm Yuvraj.
I'm Ankur.
and we will be explaining you how this robotic arm works. So we are using these potentiometer knobs to control these servo motors manually. So we are controlling it by placing 4 servo motors SG90. One is at the central axis, the other for the forearm and third for the arm and fourth to hold the gripper. So here are 4 knobs. These 4 knobs are potentiometers. Well, they control this manually. And we also have a feature which plays, pause, and replace the what we have done before. So this is the wiring. The Arduino pins and all other pins are connected. This is the push button and a resistor with another resistor to control the flow of current. The wires are into the breadboard. The connections are perfectly connected and the servo motors are connected into the 3D printed model. So we have this model right here. It has the servo motors, the wires coming out of it, and they are connected well. And it is a functionable model, which and all the potentiometer works as well, which is actually a quite good thing, I think. And the breadboard connections are perfect with the capacitor at the perfect place. And this is the DC jack. It gives the 5 volt and 3 ampere current to actually use this robotic arm. And that's it. So our problem statement defines a problem which is faced by many workers in small scale manufacturing and packaging units. It is about how they find it hard to manipulate and position lightweight products more precisely and with less strength. So to address this challenge, we made a robotic arm. This robotic arm is being developed to assist with accurate and efficient handling operations in industrial environments.
So now the target customers are the workers in small scale manufacturing units, the packaging and assembly operators, and the users or the common people who have to perform repetitive pick and place tasks, the workers who need accuracy and consistency to perform their tasks, the operators facing physical strain. So now the other stakeholders include the factory supervisors who supervise the workers in the factories, the production managers, the small business owners, and the safety regulators, quality inspectors who inspect the quality of the tasks, and the maintenance technicians and decision makers.
So we interviewed 4 stakeholders about what their needs were for this robotic arm. Our questions were what type of tasks are performed, what difficulties are commonly faced, how the error works, what tools are currently used, what features the user wants, what level of precision is required, how much training is acceptable, what cost range is acceptable. To which they replied that they want repetitive manual pick and place and positioning tasks to be performed by the robotic arm. And the difficulty that they commonly faced was hand and wrist fatigue, shaking, and reduced accuracy over time. So now I'll discuss how the error works and what they replied to this question. Errors cause delays, rework, and slow down the workflow. The tools used were manual handling tools and they were very basic tools. What features do users want? They want smooth movement, stable grip, and simple control, and they want it to be done in a limited period of time. What level of precision is required? That's 3 to 7 millimeters. How much training is acceptable? It should be less than 15, so they don't have to train the workers to use it. What cost range is acceptable? It's around 5,000 to 8,000.
Okay, so now I'm going to discuss the design requirements of the robotic arm. So the robotic arm should handle at least 150 grams of weight, shall achieve plus minus 5 millimeters of placement precision, should complete the pick up and place task in 10 to 15 seconds. The robotic arm cost should less than 8,000. The robotic arm should fit within 25 to 25 workspace. The robotic arm should operate continuously for at least 1 hour.
So this is our circuit diagram. We connected 4 SG90 servo motors, 4 potentiometers, Arduino Nano, 2 push buttons, 2 resistors, a capacitor, and a 5 volt 3 ampere DC power supply. This one is to save the motion, and this one will replay the motion on loop. These are the sketches of our engineering. So these are the design functions for the mechanical system: lightweight 3D printed base, arm links and grippers. Multiple joints allow rotational movement and a stable base. Designed for handling lightweight objects. For actuators, we use servo motors, SG90 motors. Servo motors mounted at each joint. Each joint has a 2 degree of freedom. Each servo controls one joint angle. provides smooth and precise motion, enables pick and move place actions.
For the electrical system, we are using Arduino as the main controller and servos that are connected by signal, power and ground. External power supply to power those Arduino and a proper grounding for reliable performance. Unique features of the design. It's low cost, lightweight, it has a precise control for accurate movements. The design is easy to repair, it's beginner friendly, and the quick learning curve is minimum. You need minimum requirement, minimum training to work on this. It has stable and reliable operation for repetitive tasks. It's scalable design for future. So this is the Arduino code. So this is the block code. It actually explains the logic of the code. So when we start, it initializes Arduino and servos and set them to home positions. Then it reads input button states whether to record, play, pause, or manually control it. So which mode is actually active? So if we choose the record mode, then it reads port value, remove servos, and then save angles to memory, and then repeat control loop. If we choose play mode, it fetches stored servo angles and execute move sequence, and then again repeats control loop. There is also a third mode, which is pause mode. At pause mode, it holds for arm movement. So this is our design evolution, how our design initially was and how it turned out to be. Our initial design was robotic arm controlled by Bluetooth and a mobile app. So the problem was that mobile app was inconsistent. So we used a first design change, that was switching to potentiometers to manually control the arm. So there was a limitation. The potentiometers were controlled manually. So we then again switched to a better improvement, which was adding a function that records play and pause. So the reason for addition was to allow the arm to repeat tasks, automatically reducing manual efforts. So our final outcome turned out to be a semi-autonomous automated system that. So this is our material list. We are using 4 servo motors SG90, an Arduino Nano as a microcontroller, 4 potentiometer, a PCB which we replaced with a breadboard. We are using 2 resistors 10 kilo ohm each, 1 capacitor that is 25 volt, 2 push buttons, a DC power jack, a DC adapter which is 5 volt and 3 ampere, some headers and some screws. So these are our team responsibilities. Ankur did CAD, assembly and wiring. In CAD he made central axis, forearm and the arm. Me, Hirsch, did wiring, assembly and CAD. In CAD I made the base part. For Rhythm it was report writing, final documentation, CAD and wiring, and for Yuvraj it was wiring and assembly, and he also made the base cover for the 3D printed robotic arm. So your entrepreneurial aspects are that the robotic arms already exist in the market, but they are expensive. So to counter that, our design is low cost. You can perform lightweight tasks and you can replace it. Instead of fatigue, it gives you consistency.
So the lessons learned from this whole project was that the importance of testing in design. The simplicity is often better than complexity. Also, the value of user feedback in designs. And we improved the project planning and time management. We also experienced the team collaboration and the task division. And we also gained knowledge and the entrepreneurial mindset by identifying market needs.
So the summary is to design something that is low cost and also solves a cause. And the key takeaway is user-centered and iterative design leads to practical, reliable engineering solutions. Thank you.